Any sufficiently advanced technology is indistinguishable from magic.
Welcome to this special episode called How Did This Stuff Get Here? An Inflation Crash Course with yours truly, Professor Brian Keating, co-director of the Arthur C. Clarke Center for Human Imagination and the Chancellor's Distinguished Professor of Physics at the University of California, San Diego. We're going to do a lot of deep dives into alternative theories of cosmogenesis, so I thought it would be important to take you on a ride through the standard orthodoxy, the lore and the literature of what we know about the dominant aspect, the dominant paradigm of how the universe began, at least up until about a trillionth of a trillionth of a trillionth of a second or so after the cosmic genesis event. So it's probably as far back as we can go, and with tools like the Simons Observatory, we do hope to make progress to perhaps constrain or rule out perhaps models of inflation. We'll talk about that in future videos. But today I want to give you a crash course so that you, my beloved audience, can have an insight and understanding as what does inflation do? Why do we need it? Why is it considered so successful, so much so that it is the dominant paradigm in terms of our understanding of the earliest epoch in cosmic history? And really the answer comes into play when we consider the question of how did all this stuff get here? How did the molecules, the matter that matters, us, etc. get here? How did our planet get here? How did our solar system get here? How did our galaxy get here? And so here's an example of what we call the cosmic wallpaper, at least in visible form, the Hubble Deep Field, where every single speck of light in this image, this magnificent image pointed at the universe's darkest corner, according to the Hubble telescope director back in the 90s, staring there for 2 weeks on end, revealed that every single speck of light here is a galaxy, not a star in the Milky Way galaxy, but a proper galaxy itself, which could claim to be exactly just like our galaxy, hosting perhaps half a trillion stars. And doing the math, this image subtends only about the size of your fingernail held up at arm's length, or maybe even less than that, on the whole sky. So to determine the number of galaxies there are in the universe, all we have to do is count up how many sizes of your fingernail would it take to cover the entire night sky. So this video will go on for about a couple of weeks, so let's go on and count up how many times we have to move our finger. No, we're never going to do that. But instead, we do a calculation. It comes out to be about 500 billion galaxies, each hosting maybe 500 billion stars, each of those hosting maybe 10 or 100 or 1,000 small bodies, large bodies, planetary-sized bodies, etc. So the numbers become astronomical, and the question is, how did it all get here? And that is the stuff of inflation. So inflationary cosmology is a paradigm that predicts an early, ultra-fast exponential expansion of space-time itself, sometimes called the universe. Now, it has many, many features that we'll explore in this video, and then we'll go into deep dive into some of the observations that lead to our credulity in something like inflation in future videos. But today I want to present to you the problems that emerged in the standard Big Bang narrative that inflation does solve in a very self-consistent, stable way that led cosmologists to really take it seriously starting in 1980 with Guth and Vilenkin and Starobinsky and others predicting more or less similar features, which turned out not quite to work, as we'll explore, and needed to be corrected by future pioneers like Andre Linde, who we spoke about in this video, the nature of faith to a physicist. And he is also the co-originator of the most dominant form of the multiverse paradigm, eternal inflation. We'll talk about that as well. But also Paul Steinhardt, who's been a guest on the podcast many times, has made fundamental contributions to the theory of perturbations in the early universe, which lead to structures like the Hubble Deep Field, like us. So we do need to take that seriously. Paul has vehemently opposed the multiverse outcome of inflationary universe that we talked about in The Faith of a Physicist. There'll be more on Paul's preferred cosmological models and where other alternative models like those of Sir Roger Penrose, winner of the 2020 Nobel Prize, where those could actually enter in and be tested against cosmological evidence. So inflation expands the universe exponentially in a very, very brief period of time, perhaps only a trillionth of a trillionth of a trillionth of a second in length. It makes the universe, the space that we can see, very small compared to the total amount of space that there is in what you could consider the universe, or maybe even predicts unavoidably the existence of a multiverse. Now, it does make predictions, many of which are testable, some of which make it falsifiable, despite some claims to the contrary, even those I discussed in The Faith of a Physicist, where I did say this quote that, of course, if the universe turned out not to have spatial flatness, that would have falsified inflation, but not necessarily falsified the multiverse. So it's important to separate the multiverse from inflation, and we'll make that clear in future videos. So, we'll go through, as I do with my cosmology students as undergraduates, this is a crash course in inflation. This is going to explain to you everything I want you to know about inflation in terms of its theoretical predictions, so that we can then progress on to experimental tests of some of these conclusions that unavoidably come from inflation. So, the first conclusion that we talk about is that the universe is composed of objects. These objects, galaxies, quasars, etc., they allow us to test the properties of the early universe and go back to a very, very early primordial state. Those galaxies, those quasars, etc., can have us understand how the universe originated if and only if inflation comes along with a mechanism to predict how the inflationary fluctuations turn into large-scale structure like galaxies and quasars that we can observe. Another relic that we talk about here are so-called BBN, or Big Bang nucleosynthesis observables. These are leftover fossil relics from the early universe. And some of those persist not only from the first 3 minutes after the origin of time, if indeed time began with the Big Bang, a topic that we will discuss in great depth on this channel, but also the universe persisted after that period of time in a pretty boring quiescent state for perhaps hundreds of millions of years, and then it formed primordial gas clouds. Primordial gas meaning the very first atoms, the hydrogen, helium, and their isotopes, deuterium, helium-3, those all formed into atomic versions and some molecular versions that can be observed via their absorption spectrum as long as there's something to kind of provide light to be absorbed. And we'll talk about that in connection to a late great colleague of mine, Arthur Wolf, who passed away sadly about 7 or 8 years ago. And Arthur made contributions, titanic contributions, to the study of these damped Lyman alpha systems and other objects that allow us to measure the very first primordial atoms in the universe. And those give us credulity in the origin theory that posited that the universe underwent a very brief but intense fusion reaction in its first few minutes of existence, perhaps. And that could be existence in our current universe, emerging from a collapsing universe, or it could be in the aeon or eon theory of Sir Roger Penrose and the conformal cyclic cosmology. All of which we'll discuss, especially as this is the 90th anniversary of the birth of Nobel Prize winner Sir Roger Penrose. But the Big Bang, for all its successes listed here, has many lacunae, or lacks, or gaps. Some of those involve the fact that the universe has certain properties that are unexplained, if not imposed by fiat. And cosmologists hate fiat. It's another word for God. It's another word for faith, perhaps, by insertion of external conditions that then determine the initial conditions of our universe. We'd like to do away with that, especially for many cosmologists who don't believe in some supernatural designer, as we talked about with Stephen Meyer in the Return of the God hypothesis. And we'd like to find a naturalistic or materialistic origin story for the universe, but we still have to explain these many lacunae in the Big Bang framework. One of which is the so-called flatness problem. The universe has what's called spatial flatness. No matter how big you make a triangle in the universe from something on the Earth's surface or just above the Earth's surface, any 3 points that's not on the spherical surface of the Earth that's suspended above it, those 3 points will have interior angles whose sum adds up to 180 degrees. You can make those triangles as big as planets, 3 different planets in our solar system, 3 stars in our galaxy, 3 galaxies in our universe. No matter what size triangle you make, even going back to the oldest light, the CMB itself, no matter how far you go back, any triangle will always have interior angles summing up to 180 degrees. And that's mysterious because of all the different shapes that space could have, as shown on this slide, the flat one, the one on the far right, where it's essentially Euclidean, is in some sense the least probable. There's only one shape of space that has 0 curvature, and that is flat. And those obey Euclidean postulates that parallel lines don't meet, that triangles' interior angles sum up to 180 degrees. But on a sphere, you can get widely varying interior angles of a triangle up to over 900 degrees inside of certain triangles. So it's important to think about this in the context of cosmological models. How do you get a flat universe from your cosmic theory? And all theories of cosmology, if they want to contend for the right to claim a theory of cosmic genesis, they all have to predict, as an outcome, spatial flatness. And we'll explore that for alternative cosmologies in future videos. The universe also exhibits a lack, so-called lack, of magnetic monopoles or other topological defects. We've talked about that in the past, and we will explore that in some detail as especially pertains to alternative models of cosmogenesis, and we'll explore that, the consequences of that later on in this video. The last problem that inflation successfully describes is the so-called horizon problem, which is the observation that the universe is isotropic. It looks the same in all directions. Not perfectly, you won't see a mirror image of yourself if you look out over there, but no matter which direction we look, the temperature of the cosmic background radiation, as explained in previous videos, is identical to a few parts in 10 to the fourth. So in a few parts of 100 microkelvin, really, really minute levels of cosmic temperature fluctuation, the universe looks exactly the same in that direction as it does 180 degrees behind me. Even though those two regions of space and time are separated by some 92 billion light years. In other words, they're separated by more distance than the speed of light times the elapsed age of the universe times a very large factor. These are puzzles that every cosmological model that wants to claim the title of cosmic genesis description, and genesis not meant in a religious sense, but just in the description of the origin, initial conditions of our universe, they have to contend with that. And it's not clear that other solutions will be able to, other theories will be able to provide the solutions as economically, as parsimoniously as inflation seems to have done. Of course, inflation is not without its critics, and we'll explore the consequences of both its critics and its potential successor theories later on in this channel. What is the flatness problem? So it was a problem observed and thought to be quite fatal, at least in the Big Bang model in the 1970s. And there was really kind of a paradox that for almost all time, with a universe that contains matter and radiation that we know exist in our universe, no other exotic phenomena, no other exotic dark energy which we know exists, or dark matter, just us, the stuff we're made of, baryonic matter, and radiation that we see from the CMB, cosmic microwave background radiation. A universe with matter should not have flatness unless it was exactly isotropically established at some extremely early time. So the equations are shown here. I'm not going to get into all the great detail, but the laws of physics can involve a wide variety of very coarsely tuned, not fine-tuned value at all. But we seem to choose a value for the curvature of space-time, the interior angle of triangles, always summing up to 180 degrees. That feature is an observable that has been unavoidable since measurements done by Princeton University's Lyman Page and my late advisor Andrew Lang at Caltech in the Boomerang experiment with Palladio Bernardus and others, that the universe's flatness, established very firmly by cosmic microwave background experiments, seems to indicate that we live in a very improbable universe. And it actually gets worse the closer you go back in time to the Big Bang event itself, or even just till you go back to the time at which the universe became a fusion reactor and produced the sorts of elements that we observe today. So we observe elements at high redshifts in the form of hydrogen molecules, deuterium, etc. And we observe those in clouds of gas that somehow collapsed and condensed, and they're not just evenly, uniformly distributed. And the question is, how did that get there? Well, they must have come from a very hot, dense period of time called Big Bang nucleosynthesis, when the first elements were synthesized, including their isotopes. Like deuterium is an isotope with 2 neutrons of hydrogen. If we look back to when the universe was creating the deuterium and the hydrogen, the fusion reactor that was putting together these neutrons with protons, or protons with protons and neutrons to make helium, protons and neutrons attract each other via what's called the strong nuclear force, but protons and protons which should repel each other, and it takes the strong nuclear force and force between quarks to cause them to bind together. Nevertheless, that took place at extremely high temperatures, extremely high densities, and then the universe cooled off. So the question is, how did the universe go from a density, a description called radiation domination? We can go back to this very tiny fraction. It actually makes the problem of the universe's curvature, as shown in this equation 10.11, where the equations reference my friend Barbara Ryden's book. And these equations are connected to her book. I urge people to get it. It's very readable, even for a lay audience. This equation shows that the universe was even more flat as you go back in time to earlier and earlier epochs. And the problem gets worse and worse as you go back in time as close as you want to the origin of the universe itself. So something must have established the universe in a flat initial condition almost from its inception, such that today, 13 billion years plus later, we would observe it with an uncertainty of about 0.5% in its curvature. In other words, the universe could be approximately 0.5% curved, 0.5% positively curved, 0.5% negatively curved, although that will be driven closer and closer to zero as you go back in time. So in other words, the fine-tuning of the initial curvature of the universe at whatever time period you want is almost exponentially challenging to explain unless you put it in by hand, which we don't like to do. We like to have a physics explanation, perhaps from a theory of astroparticle physics, perhaps from some other theory. We don't necessarily like to impose the imposition of a mind at work. So the universe had this very, very unusual initial condition. Of all the conditions it could take, from all the different radii of spherical surfaces that could have taken on, which are infinite, from all the negatively curved surfaces that it could take on, Pringle-shaped, hyperbolic-shaped, saddle-shaped, there's an infinite number of those. So there's an infinite number of positive curvature, infinite number of negative curvature, and we happen to live in the one example of flat curvature. That needs to be explained. So the Big Bang had a challenge to it. And it was realized this was a significant challenge as early as the 1970s. Only a few years after the discovery of the CMB itself, which we'll talk about and how it originates in the inflationary paradigm, and what it can teach us via its B-mode polarization that my colleagues and I study using the Simons Observatory. Now, the other problem that was very vexing to cosmologists was the so-called horizon problem, which is this facet that no matter which direction you look, for the left or the right, forward or backwards, the universe has almost the same exact temperature to a part in about 10,000. So a 1 part in 10,000 is about 5 to 10 times smoother than the highest mountain on Earth compared to the Earth's radius. So the Earth has a radius of several thousand kilometers. The highest mountains are a few kilometers. So you're talking about a similar or smaller amounts of fluctuation in the temperature of the microwave background compared to the surface of the Earth, which is quite ragged and rough, right? But even so, seen from space, it looks almost perfectly smooth. The universe is even more smooth. It's smoother than the surface of a ball bearing, of a bowling ball, whatever choice of sphere you could make. It's very hard to make something smoother than 1 part, or more isotropic than 1 part in 10 to the 4th or 10 to the 5th. So two antipodal points, two different directions you look, have the exact same temperature for all intents and purposes. How could that possibly be? When the universe was in its infant state, and even when it was in the age of 380,000 years or so, when the CMB was produced from the combination of proton and electron to make atomic hydrogen, releasing and allowing photons to freely propagate to our telescopes today, that epoch, 380,000 years after the Big Bang, it's impossible for the entire universe to come to thermal equilibrium at that time. Imagine changing the temperature of the universe right now to make the universe all the same temperature, all exactly 3 Kelvin with a fluctuation of 10 to the minus 4, 10 to the minus 5. That would be incredibly difficult to do today, and it wasn't that much easier when the universe was a factor of 1,000 smaller. It was a little bit easier, but not nearly easy enough to explain this bizarre phenomenon that no matter what direction we look, even two different directions that have never communicated with each other. Again, if you're looking at the sun, you can look at the sun, wear protective sun eclipse glasses, please, take it from your friendly neighborhood astronomer. It will not be able to be possible for Pluto or for Neptune to receive the information that you're now receiving if they're on opposite sides, because Earth is much closer to the sun than is Neptune, so it takes light longer to get to Neptune, and yet it would be like all the planets are at the exact same temperature, established instantaneously. We don't understand how this took place in the standard Big Bang. That's one of the things that inflation purports to solve. Observations from the CMB, as I say, demonstrate that the universe has fluctuations, but those fluctuations are tiny. The temperature in one direction differs from the temperature in the other direction by at most a fraction of a millikelvin, 1,000th of a degree Kelvin, over the whole sky. Once you get rid of the pernicious dust effects in the Milky Way galaxy described in Losing the Nobel Prize and other videos that I've discussed on this channel. So we know this from temperature anisotropy measurements. We know that the universe is flat from temperature anisotropy measurements, this so-called Doppler peak that is shown here. But the question of why this image of the CMB, this map made from the Planck satellite data, why is this so homogeneous, so isotropic, it looks the same in all directions, it's almost too good to be true. We assume the cosmological principle holds, that the universe is isotropic and homogeneous on large scales, but that's kind of an assumption that we get from observations. But the reason why we can make that assumption is not at all clear. We have no primordial theory that mandates that it should be so, And inflation is one of the best candidate models for it. There are actually only a few different candidate models for cosmogenesis, for the initial conditions establishing the formation of light elements, solving the flatness horizon, and the monopole problem that we'll come to next, besides inflation. Maybe a handful, maybe 3 or 4 at most. And inflation is certainly the most successful. So why are these regions all the same temperature? Maybe it's just a coincidence. So it turns out that you'd have to have a coincidence to make this that is essentially straining credulity. So here, this image my colleague Andy Friedman, my late great colleague Andrew Friedman made. This sphere on the right shows a tessellation, a triangulation, if you will, into as many different circles as you can fit and still see it on this diagram. And the question is, the temperature inside each one of these little circles here has almost the same value to a part in 10 to the 4th or 10 to the 5th. Now this is an exaggeration, more coarsely grained than the image on the far left of the screen, which shows the actual CMB, but this is just for illustration purposes. It turns out you can divide the sky, the entire sky, any sphere, into over about 40,000 patches. 44,000 square degrees is how big the night sky, the full 4 pi steradians, subtends when converted to square degrees, and you can divide it into patches as shown on this previous slide here. The peak of the microwave background occurs at about 1.12 degrees. So in other words, the horizon at last scattering was only about 1.12 degrees. So roughly there are about 40,000 patches of sky of the size of the horizon at last scattering. And they all have the exact same temperature to within our measurement ability to within about 1 part in 10 to the 4th. That's a great puzzle, because ideally they should be kind of randomized with much larger fluctuations, and yet they're very, very close to one another. And so the analogy that we like to use is if you have like a dinner and you have a potluck dinner, and you get together with your friends, you invite 40,000 of your closest friends to Petco Park here in San Diego, and you say, bring a dish, you don't tell them what to bring, and they all bring that same disgusting marshmallow thing over here, a potato salad or whatever that is. I wouldn't want to eat it. I don't recommend you do either, but the point is, if all 40,000 of them or so bring it the same exact dish, you would suspect some kind of conspiracy at work. And that's effectively in the CMB context saying that there was a equilibrium event that occurred prior, much prior to the surface of last scattering's production, earlier than 380,000 years or so after the Big Bang. And there was something that synchronized all the temperatures to the exact same temperature within a tiny fraction of a degree of a millikelvin. And that was synchronized. And it turns out you have to synchronize it much, much earlier than the time of the CMB, because there's not enough time at 380,000 years to get the conspiracy to work. You have to set it much, much earlier. And inflation is one of the mechanisms by which this conspiracy can be had. Another example that we sometimes use is if you have these islands that have never been visited, they're widely separated, and yet they speak Portuguese or something. You'd have to think that sometime in the past they were visited by the same Portuguese colonists. And so it becomes hard to dismiss it as a coincidence, and so you look for a physical explanation. So the horizon problem is this very statement that this pattern here, although it looks kind of modeled and variegated, it's actually very, very exaggerated so that you can see it. Actually, the fluctuations are very small. The universe is very smooth at this time, 370,000 years after the Big Bang. So all of these regions of the universe were out of causal contact pretty much, unless they're within 2.3 degrees or so of one another on the sky. And again, if you look in the direction right in front of your nose in the microwave background and look 180 degrees around, you still get the same temperature coincidence, even though those are much, much greater separation than 2.3 degrees. It's a great mystery. Here's a diagram that Andy Friedman made with his colleague David Kaiser and Jason Galicchio, who's a professor at Harvey Mudd College. David Kaiser at MIT has been a guest on the podcast. And it shows what are called light cones intersecting in the past. And the question is, how far back do you have to go so that two events share the same causal history? Meaning you could turn the temperature in this corner of the universe and turn the temperature in that corner of the universe and allow them to get, by the time you make an observation, to the same temperature without having to violate any laws of physics, such as faster than light information transmission. So Andy did some of these calculations. I'll leave this on the screen. And it turns out to be incredibly hard to do beyond this 2.3 degree separation. And of course, this diagram is not the scale, but Andy could easily show, and you can easily show just by inference, that 180 degrees is some 90 times almost harder than 2.3 degree separation. So there's really no explanation other than some of these other models that establish a prior period of thermal equilibrium to explain the so-called flatness problem. It's a major, major prediction of the inflationary paradigm. So this is the horizon problem. We described the flatness problem. These slides I'll leave up on the screen so that you can pore over them in the depth that they deserve. So these circles are projections of the light cone back to a surface of last scattering. Again, Andy is indicating they're not to scale. The last problem that counted originally as one of Alan Guth's major motivations was to explain the absence of so-called magnetic monopoles. So if you combine the fact that the universe began to fuse elements together 3 minutes or so after the Big Bang, you can unavoidably extrapolate to earlier periods of time when it was too hot to form quarks or form protons, certainly, and that temperature was high enough that you could actually go through what's called a phase transition. The phase transition is very similar to a transition from ice to liquid water or from liquid water to steam, going from one form of matter to another. And typically at the boundary between, say, melting ice into water, there'll be some surface, some chunk of ice that's broken off where there'll be a boundary. And that is sometimes called a topological defect for interesting reasons. We're not going to get into that. But it's a phase boundary between liquid water and solid water, i.e. ice. And that boundary has certain properties that in these theories in which you unify the strong, weak, and electromagnetic forces of nature produce what are called monopoles. So an ordinary magnet, a horseshoe magnet or a bar magnet, has a north and south pole. If you break that horseshoe magnet in half, you don't get a north pole and a south pole. You get a north pole and a south pole and a north pole and a south pole. In other words, you've doubled the number of north poles and south poles. And from Maxwell's equations, we know that monopoles never occur in nature. But the question is why? If the universe underwent this electroweak unification, this phase transition in which magnetism and electricity are still unified at temperatures associated with, even with very high temperatures like the sun or something like that. But if you go back to 10 to the 12th GeV, a trillion times higher than what CERN's LHC can probe, if you go to those extremely high energies, electromagnetism and the weak nuclear force were one force, and perhaps they were combined with the strong force as well as what's known as a gut. We've talked about theories of everything, and I joke sometimes we think about the toes more than we think about the guts, and that is sort of this notion that we want to outdo what Einstein did, and we have many videos with Eric Weinstein, Garrett Lisi, Stephen Wolfram, and others that purport to come up with other ways to unify gravity and quantum mechanics. And of course we did this video on loop quantum gravity as well, which is a candidate theory for quantum gravity, if not a theory of everything. So the electroweak phase transition and the gut theory perhaps occur at temperatures associated not with 3 Kelvin or 3,000 Kelvin or 3 trillion Kelvin, but something like 10 trillion Kelvin or more. And so these are just completely out of the reach of any kind of particle accelerator or Bunsen burner that you may have access to. And so it's many, many orders of magnitude. In fact, it's coming close to the what's called the Planck energy, and that may be the ultimate discretization energy, the ultimate highest energy that anything could ever achieve. So we'll explore some of the consequences of all of these, but inflation is a paradigm which can purport to explain the monopole problem, the flatness problem, and the horizon problem. We have to take it seriously. We don't have to accept it as it is. We can propose modifications. It too, just like the Big Bang had lacuna, so too does the theory of cosmic inflation. And some say those lacunae are fatal. In other words, some say the existence of the multiverse and the fine-tuning that's inherent in inflation requires either some imposition by fiat of a low entropy state or the addition of some period of collapse, contraction, or perhaps these infinite expansions of the aeon theory of the cosmic conformal cyclic cosmology. We'll talk about those more. For now, This has been your crash course in the problems of the Big Bang that lead us to believe in inflation. Next time, we'll talk about the actual nuts and bolts of inflation, and I'll give you a crash course in the ins and outs of what a professional cosmologist does as a theorist, and then how we're trying to probe these predictions, including some new predictions, using cosmic microwave background polarization experiments, such as the Simons Observatory. Stay tuned for more. Signing off now for Into the Impossible, I am your fearful host, Dr. Brian Keating, Chancellor's Professor of Physics at the University of California, co-director of the Arthur C. Clarke Center for Human Imagination.
If you enjoyed this video, you definitely want to check out this playlist with my cosmology friends talking about the origin and evolution of the universe. And if you're interested in a deep dive in the multiverse, wormholes, and other exotic phenomena, click here and hear my conversation with Juan Maldacena of the Institute for Advanced Study. Enjoy! And don't forget to subscribe for more amazing content.